So yeah, we're right up on this. So our next speaker is me, actually. Surprise, surprise. So I'm gonna see if I can get my screen share up here. Because in the desperation to get everything else set up, I haven't tested this out yet. So we're about to find out if this works. Yeah. So here's to experimentation. Yes, awesome. So y'all can see that there. All right. So functional and object-oriented programming, diametrically opposed concepts, right? I mean, we have functional languages like Pascal and Clojure and Elixir. Then we have object-oriented languages like Java and C Sharp and C++. So which one's Python? Well, Python, everything is an object, so it must be object-oriented, right? But then you look and you see things like closures and lambdas and immutable strings, and then you begin to wonder maybe it's functional. When in actual fact, Python is both. It can do both paradigms and many others besides. But the way it's implemented these paradigms allows you to combine the best of both functional and object-oriented programming to create some pretty resilient code. And that's what we're going to be talking about for the next 20 minutes or so. So if somehow you have missed it, my name is Jason C. McDonald. I'm also known across the internet as CodeMouse92. And that book we've been hyping up the whole time here is actually mine. So recently published from No Starch Press. So if you're looking for an explanation of the entire core language of Python, whole thing, without being dragged by your teeth through the basics of coding 101 all over again, this is the book for you. And I go through, I guide you through the whole core language and the whys and the wherefores of idiomatic practice. Everything I'm going to talk about in this talk is in the book. So if you want more detail, definitely check that out. Okay, so object-oriented programming, what is that? Well, the big benefit of object-oriented programming, the reason why it's stuck around for so long, is encapsulation. It's a great way of organizing related data with the methods that modify that data. And you don't have to understand how it's actually doing it inside the object. It's just you put in some data, you get out some data. Pretty straightforward. Objects and classes are really reusable. You can instantiate multiple objects. You can reuse bits of code from different classes using inheritance patterns. So you get a lot of dry, don't repeat yourself type patterns. And when you're writing good classes, you should bear in mind the single responsibility principle, or the S in that solid acronym everyone throws around, which is that one object or one class should have one clear responsibility. But there are some downsides to object-oriented programming. Common complaints include that it's unpredictable. You don't necessarily know when or how these objects are interacting with each other. And it can be hard to even see where data comes from, where it goes to, because everything is made up of these black boxes that you can't see inside of. It can be very difficult to start figuring out where a change occurs to some piece of data. That's when black box starts fighting against you. We call it ravioli code. Generally, once you get inheritance involved, you just get this big hairy mess. You inherit the multiple inheritance, and it gets really complicated if you're not very careful. And this has led a lot of people to just demonize object-oriented programming as a horrible thing. The answer, they say, is found in functional programming. So functional programming brings with it this concept of purity. No side effects. You pass in a value to your function, and you know that that value itself is not going to change. Function is going to return something else. It's stateless, so a function is not going to depend on any external state. It's only going to care about the data that was passed to it. It is repeatable, so you pass in the same value to the function, you should get the same output every single time, which is great for testing, by the way. Functional programming is very, very testable. It's isolated. One function doesn't really care how the rest of the code is implemented, as long as the functions it relies on have not changed what they're returning, then it's just going to keep on working no matter where in the code it lives. Functions are reusable, obviously, and you can apply the single responsibility principle here too. One function has one responsibility. Names are a great hint, by the way, of whether or not you're violating this. If you need the word and anywhere in your function name, you got a problem. So this makes it sound like functional programming is the answer to the life, universe, and everything. But there are some downsides here too. Performance, immutability, meaning never modifying an object, is really a bad thing when you're dealing with very large bits of data, like a NumPy array, a pandas data frame, a very large image. Making copies of that is expensive. And so it's really impractical for, say, data science. It's not great for GUI because GUI is very stateful. You have all of these bits of state that have to go somewhere. It can be hard to think about structuring functional programming because you have to figure out how you want to organize your functions. But more importantly, where's that state going? When you have some piece of data, you need to keep track of where do you put it? Where does it come from? You might be tracing your way through a long chain of functions, and that can get rather obnoxious after a while, especially when you have multiple pieces of related state, which is when it becomes a problem. So this isn't necessarily the answer to everything, but functional programming does solve a lot of problems. The biggest advantage to it is purity. It just makes your code a lot easier to reason about, a lot easier to test and verify. Object-oriented programming brings structure. So a rational, kind of organic way of laying out your data that just makes inherent sense. So it's not really the demon that some people like to think it is. So we're going to talk about how to combine these two together. So to understand how object-oriented and functional can work, we have to remember that objects encapsulate data. No, strike that. We're talking functional. So objects encapsulate state. Multiple pieces of related data that make up state can be encapsulated together into an object. Now, there's two ways that we can approach this. One is predictable mutability. We're wanting that predictability of functional programming, so we have to respect purity. So there's some patterns we can use to do that. Or we can use more immutable objects, which is a thing in Python that a lot of people do not realize is possible. We're going to talk about both of those. We're going to start with predictable mutability. So with functions, functions always have to be pure, meaning they don't modify their parameters. There's no side effects. If I pass A to a function, A should not change. One exception to this is that a method may mutate self. A method belongs to a class, and so a method can mutate self. This actually makes sense visually because you see that A is not inside the parentheses on that second line there, it's in front of it. So that A dot and then whatever can start becoming syntactic sugar for A's getting modified. It's the same as reassigning, like we see here, B equals F of B. B is obviously being mutated. It's being changed in this case. So we can consider these to be somewhat equivalent bits of syntax. You can use a lot more properties too. I really love properties because this first one, this is just a getter that is disguised as an attribute on an object. Calling a.x, obviously it's not going to change anything. It shouldn't change anything. So there's no surprise there. We're just accessing something. Whereas the setter through a property, a.x equals 6, that is changing x, or a, well, changing both. You would expect that because you see the assignment. So it becomes a lot easier to spot when you're changing things. Downside to properties, you can't really pass multiple parameters to it. But you can usually get around that problem, and in most cases, you just have to think about your code a little different. Optionally, you can set a rule for yourself that your methods have to mutate self. That is that you come to expect that if you're going to call a method, that it is going to mutate the object you're calling it on. So if you don't want to mutate A in this case, pass it to another function or pass it to a class method. This way, you can see it's inside the parentheses, and that's kind of a guarantee it's not going to get changed. In case you're wondering if this works, I actually did apply this in a production grade data science project involving huge, huge images. And it does work. There's a lot of state involved in that project, and this pattern really did work. So when you're following those rules, then you can add one other rule to your mindset with functional, and that is don't call methods on arguments. If I'm taking X as an argument, I can access the property, I can pass it to another function, but I should not call a method because that could be mutating. So I don't do that. The exception, again, is on self. We can always mutate self. That's fine. You also want to avoid assigning, especially mutables, because think about it. You've probably seen this before. If you pass a list to a function and then you append to that list, you modify the list you passed in, which is bad. So as a rule, just don't reassign, because what's happening here, in case you aren't familiar, is you're creating an alias. A and X now point to the same object in memory because X is a list and it's mutable. It can be changed. So that could be a problem, because now if I mutate A, I'm mutating X. Not good. But if we pass it to something else like copy, that's returning a copy of X, and then I don't have to worry about that so much. Now, what about statelessness? We're actually okay here. Methods do not rely on external state. They're using the state being passed in on their arguments because self is an argument. So we don't actually have to create global state. We can continue to avoid that. Possible exception may be if you're working with GUIs, you may have to fudge the rules a little bit there, because doing GUIs without global state is a little hard. Not impossible, but difficult. And by the way, if you're wondering if this is violating functional at all, we already excused closures on this point. You can write a function that returns another function that is closing over the value that was passed to that outer function. That's okay. We've been doing that in functional. The closure language is literally the name for this pattern, and that's functional. So that's okay. It's all right if a function is containing some state that was explicitly passed to it. All right, so before we go further, just to hammer this point home, functions do something. They perform an action, whereas objects are something. The talk I gave a couple of years ago called "You're Doing Classes Wrong and So Is Everyone Else," I talked about how classes should be defined by their constituent data. Never create a class on the basis of what it does. Create it on the basis of what it is. So let functions be your verbs and objects be your nouns, as it were. So object-oriented programming brings with it organization. Objects can encapsulate state, which could consist of multiple values potentially. For example, I'm loading an image from a path. That image object might actually contain the loaded image itself as well as the path to that object. I can then mutate that state internal to the image object. For example, removing the alpha channel from the image. I could also make conclusions about that state. I could expose a property called dimensions, and that returns the dimensions of the image. So there's no need to, So all of this can go inside of the object, and there's no need to understand how it's doing it, as long as we understand what functionality is being exposed. So that's where encapsulation comes in handy. Mutability, how do we take advantage of this when we're not able to modify on our parameters? Well, we can allow a function to own a heavy object as long as it's acquiring that object. So in this case, we're passing path and rule to F, and we can use those, but we're not modifying either one. F, however, is calling another function that's getting this heavy object. Maybe it's creating it, maybe it's just getting it from another function, but it is owning that object. Since it owns it, it can use mutability. So we can mutate on heavy, do whatever we want with it. And then we could return a lightweight result. That would be fine. Or we could return the heavy object and never mutate it again. Or actually, correction I was going to make to the slide and I didn't, is if I'm calling f from inside of another function, as long as that function is owning that object, it's the one actually calling it, then I can mutate it all I want to because it's not being passed as an argument. So see, you can actually work with this in the functional patterns. It just requires a slight shift in your architectural thinking. And again, I've actually used this pattern in production. It is possible to do. So the benefits of this are threefold. Functional programming gives us nice testability, purity, less surprises. Objects allow us to organize code, which is great, organic organization kind of patterns. And then mutability gives us good performance when we're dealing with large, complex data. So that's all great for predictable mutability. What about immutability? Python's got some immutability like integers and strings. You can't mutate those objects. They just are what they are. Once they've been defined, they can't be changed. And this really blows past a lot of these problems because you can't modify something that you can't modify. It's pretty straightforward. So if we can write some classes of our own that we cannot modify, then that's going to make our code a lot more resilient because now we're getting error messages instead of just bugs. So here's the point at which I'm actually going to program this instead of throwing some more slides at you. So I am going to bring up my editor. Bear with me for a second because I have to switch my screen share. And that should be this. There we go. PyCharm. Good times. Ignore that first line. I just have that saved because I'm too lazy to type it out again. So let's talk about a class. Let's just start by creating a class called RGB color. Let's do it the traditional way first. So in our initializer, we want 3 values, red, green, and blue. These are meant to be integers, but I'm not going to take the time to put in the hints right now. Basic initializer. And then let's do dunder string just so we can see this represented as a string, specifically as a hex code. I do love my F strings. So if you are curious what this is, look up the formatting codes for F strings. A lot of cool things you can do with them. So these are 2-digit hexadecimal numbers. Okay, so let's create color. Let's just go with white because that one's easy enough. I can print that out, and let's do black as well. So there's some easy colors that we don't have to memorize the codes for. Let's print this out here. So let's run this, and you see it prints out white is FFFFFF, black is 00000. That works. Okay, but there's a couple of problems here. I'm gonna hide this one for a minute here. There's a couple of problems because I can modify this after the fact. Let's see. Let's say I want to change red to 42. And I'm going to add a random attribute here. So let's change this to 255. So if I run this again, this is now changing. This is not that 00000 we're supposed to be getting. I'm modifying it. And that's defeating the purpose of immutability. This is what we want to avoid. We can fix this first by defining dunder slots as a class attribute. This is a list of strings of the names of the attributes, that is member variables, that you want to allow. You don't have to include your functions on here. your methods only the instance attributes themselves. So we want to allow red, green, and blue, and nothing else. So if I run this, I now get an error trying to add flirm. And this is important because one of the other advantages here, if I take away the slots again for a second, is there's this dictionary behind the scenes. This is where those instance attributes are actually being stored inside of that object. But when we bring slots into the picture, we're getting rid of that dictionary. And it's using something else behind the scenes that's a lot faster, a lot better performance, and you can't arbitrarily add to. So you cut down on errors. So you can use slots in most cases. I won't go into all the edge cases, but there are some things to bear in mind when using them. But in general, for typical objects, just throw slots on there. No big deal. So I can't add flirm anymore, which is great, but I'm still modifying this attribute. That's not good. So Python exposes nearly everything, nearly all its functionality through these dunder methods, double underscore methods. And we have one called setAttr. So what I can do here is I can take any action I want to before the value is set, because I have to explicitly call on the parent, that's what super's for. On the parent class, I have to explicitly call here we go. I have to explicitly call the setAttr there. So now you see it's telling me every time it's setting an attribute before it actually does it. So we can use this to our advantage. We can say if it does not already have the attribute, we can use the hasAttr function. If self does not already have whatever attribute key is, then we're going to go ahead and define that. Otherwise, we're going to raise this attribute error. I am copying the attribute error used by Python, raised by Python, if you try to modify an attribute on a string or an integer. So now I can no longer modify that attribute after it's been created. I can create it initially, but I can't modify it anymore. So just to prove that, comment that out, and we get 0, 0, 0, 0, 0. However, there is one other run around the rules here. If I delete the attribute first, now I can totally reassign it. That's no good. Well, we have another dunder method called delattr. We can do the same thing. Raise an attribute error. We never want to allow deleting an attribute. When the object itself is torn down, we'll let the garbage collector take care of things. So now I can't delete. I cannot reassign. I can't add arbitrary values. I can only initially assign, and that's it. Once it's been initially assigned, I can't change it after the fact. So I can have as many of these instances as I want, but they're immutable. Now, some smart aleck watching this at some point in the future is going to say, well, all I have to do, Mr. McDonald, to modify your precious class is to say object.setAttr, and then I'm going to pass in the object I'm modifying, the attribute I want to modify, and the new value. And then if I print it out again, how do you like them apples? But I would say if you're getting this clever at this point, you deserve whatever bugs you're going to get. This is not normal Python. Like calling object directly or calling the parent and actually calling dunder setAttr yourself is so strange. You should not be doing this. So it's a little bit like how we don't have data hiding in Python. We don't need it because we have this principle, as it was explained to me. You don't stay out of the living room because I have a shotgun. You stay out of my living room because I asked you nicely. So it's this principle of the programmer probably knows if they need to violate the rules, and they're responsible for the risks if they do. So if you're going to do this, have fun with the bugs. But outside of that, for all normal usages of the class, you have something that is, for all intents and purposes, immutable. And you get some free performance gains from it, which is pretty cool as well. So if you want to see this pattern, this is in the book. One other thing really fast is if you're going to do this a ton, pull the set and del adder out, create a mixin. A mixin is just an incomplete class that's got some methods that you might want to share. I can add that, and that does the exact same thing. But I can now create as many classes as I want and apply that immutable mixin without any trouble. So that is immutable classes in Python. And yeah, it really does work. So yeah, that is objects and functional in Python. So I've got a couple minutes here. If anyone has any questions for that, please go ahead and throw it in the live chat or ask speaker room on Discord, and happy to answer those. I'll keep an eye on that. But while I'm waiting on that, because I don't like asking myself questions, I'll just mention again that that book that I wrote, Did Simple Python, which I describe this and much, 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 much more. You can win a copy of that. Enter this raffle here, and you could win a copy. But yeah, that book is available from No Starch Press now, so get it wherever you like to buy your books. And yeah, so I will also be in the Discord. So if anyone has any questions after the fact, you could totally hit me up there or anywhere on the internet. I am CodeMouse92 ubiquitously, so you can